Hello everyone, myself Hans. Today we are going to solve the problem of partial differential equation. Here in the question, find the family orthogonal to function f of z into x plus y whole square in comma x square minus y square is equal to 0. Let's solve the problem. Given f of z into x plus of y का whole square comma x square minus of y square is equal to 0. This is given in the form of, and we know that this is the form of f of u comma v is equal to 0, and from here this is u is equal to z into x plus of y का whole square and v is equal to x square minus of y square, and we have to use chain rule. f of u comma v is equal to 0 can be also written in the chain form. This is using chain rule. This is written as del f upon del u into del u upon del x plus of del f upon del v into del v upon del x is equal to 0, and let this equation 1, and we can also write f of u comma v is equal to 0 with respect to y. This is written as del f upon del u into del u upon del y plus of del v upon del f upon del v into del v upon del y is equal to 0. This is equation 2, and we have to find the value of del u upon del x, del v upon del x, and del u upon del y, and del v upon del y, and put in equation 1 and 2. First we have to differentiate u is equal to z into x plus of y square with respect to x. This is given as del u upon del x. Del u upon del x is equal to, here is z is taken as the first function and second function is x plus y whole square. Differentiating with respect to x, this is given by 2 times of x plus y, and again x plus y differentiating with respect to x, this is 1 plus of x plus of y whole square, and again z differentiating with respect to x, this is given by del z upon del x, and from here this is del u upon del x is equal to 2z into x plus of y and plus of x plus of y whole square, and del z upon del x is written as p, and further we have to u is equal to z into x plus of y square differentiating partially with respect to y. This is written as del u upon del y is equal to z is taken as the first function and second function x plus y whole square differentiating with respect to y. This is 2 times of x plus of y, and again x plus of y differentiating with respect to y gives 1 plus of x plus of y whole square, and again z differentiating with respect to y. This is del z upon del y, and from here we can also write del u upon del y is equal to 2z into x plus of y and plus of x plus of y whole square, and del z upon del y is written as q, and further the value of v is given by v is equal to x square minus y square. We can also find from here differentiating v is equal to x square minus y square with respect to x. This is given as del v upon del x. This is 2x, and again v is equal to x square minus y square differentiating with respect to y. This is given by del v upon del y is equal to minus of 2y, and we have to put the value in the equation 1 and 2. First we have to put in equation 1. This is given by del f upon del u, and here is taking bracket. We have to put the value of del u upon del x. Del u upon del x is given by 2z into x plus of y and plus of x plus of y whole square into p, and plus of here del f upon del v, and here the value of del v upon del x is given by 2x. This is 2x is equal to 0. Let this equation third, and again we have to put the value of del u upon del y and del v upon del y in equation 2. So we have to write here, this is del f upon del u, and we have to put the value of del u upon del y. This is del u upon del y is given by 2z into x plus of y plus of x plus of y ka whole square into q, and here is plus of del f upon del v, del f upon del v, del f upon del v, and the value of del v upon del y is given by here minus of 2y. So we have to write here minus of 2y is equal to 0. This is the equation 4th. And equation 3rd can be also written as in the form of, this is equation 3rd can be also written as, this is del f upon del u into, this is 2z x plus of y and plus of x plus of y ka whole square into p, and we have to take del f upon del v into 2x into right hand side. This is minus of 2x del f upon del v, and we can let this equation 5th. And equation 4th can be also written as, equation 4th can be also written as, this is del f upon del u into, here is 2z into x plus of y and plus of x plus of y ka whole square into q, and here is plus of del f upon del v. When we have to take here, this is minus of del f upon del v, and 2y is taken to right hand side. This is equal to plus of 2y del f upon del v. This is equation 6th. And we have to dividing equation 5th with equation 6th. Dividing left hand side to left hand side and dividing right hand side to right hand side. Equation 5th of left hand side is del f upon del u into, here is 2z into x plus of y and plus of x plus of y ka whole square into p, and the equation 6 of left hand side is del f upon del u into, here is 2z into x plus of y plus of x plus of y ka whole square into q, and the equation 5th of right hand side is minus 2x into del f upon del v, and the equation 6 of right hand side is 2y into del f upon del v. And from here we have to also del f upon del u to cancel out here, and here is del f upon del v, del f upon del v is also cancel out, and we can also cancel out 2 to 2 is also cancel out, and the remaining is here, this is 2z into x plus of y plus of x plus of y ka whole square into p upon, here is 2z into x plus of y plus of x plus of y ka whole square into q is equal to, here is minus of x upon y, and we have to cross multiplication with this, and further we have to proceed on cross multiplication with y. This is given by 2yz, and this is x plus y, and plus of, here is x plus of y ka whole square into yp is equal to, we have to also cross multiplication minus x with this. This is given by minus of 2xz and x plus of y, and here is minus is also multiplying with this. This is minus of x plus of y ka whole square into x cube. Further we have to solve. We have to take, one second, we have to take in x plus of y ka whole square into yp, and from here minus of x plus y ka whole square into x cube, taken into left hand side. This is plus of x plus of y ka whole square into x cube is equal to, here is minus of 2xz into x plus of y, and from here 2yz into x plus y is taken to right hand side. This is minus of 2yz into x plus of y, and further we have to solve. We can also write from here, we have to take common from here, that is 2z, minus of 2z taking common, minus of 2z, x plus of y is taking common, and the remaining, the bracket is present here. This is 2z x plus y minus 2z x plus y is taking common, remaining is here x, and from here is plus of y, and we can also write here, this is minus of 2z and x plus of y into x plus of y. This is written as minus of 2z x plus of y ka whole square, and from here, from left hand side, we have to take a common. This is x plus of y ka whole square is taking common, in the bracket is present. This is yp plus of x cube is equal to, here is minus of 2z into x plus of y ka whole square, and from here we have to cancel out the terms, x plus y ka whole square to x plus y ka whole square, and the remaining is here, once again, and the remaining is yp plus of x cube is equal to minus of 2z, and this is the form of pp plus qq is equal to r form, and from here this is p is equal to y and q is equal to x and r is equal to minus of 2z. Once again, pp plus q is equal to r. Here is r is equal to minus of 2z, and we have to find the family of orthogonal. The differential equation of family of surface orthogonal is given by, this is p dx plus of q dy plus of r dz is equal to 0. This is the formula for differential equation of the family of surface orthogonal, and we have to put here, this is in place of p, we have to put here y, this is y dx, and plus of, here in place of q we have to put x, once again x dy, and this is x dy, and plus of, here in place of r, this is given by minus of 2z, this is 2 2z dz is equal to 0. On integration, this is given by on integration of dx is x, this is given by xy, and plus of integration of dy is given by y, this is also xy, and minus of 2 and z dz on integration, this is given by z square upon 2. And we can also take a constant, that is c1, c is taking constant, integration constant, and from here 2 is cancelled out, and this is given by 2xy minus of z square is equal to c. This is the required family of orthogonal to the system of differential equation. This is the required solution. 2xy, xy plus xy, 2xy minus of z square is equal to c. This is the differential equation of the family of surface orthogonal. Thank you class, and thank you for watching.